All right, today we're going to start section 1.2. We will finish it on Friday, so over the weekend you'll have 1.2 to do. It'd be a great idea if you could to get started between now and then, but it won't officially be assigned. Thumbs up? All right. So today we're going to take a look at some patterns and or some information about patterns, and where I want to start is with a little bit of language. And in particular, the reason this language is important is because you're going to see questions asking you to do things, and you need to know what they're asking you to do. So in particular, conjecture is a statement, it is a part of a lot of the questions where they'll say something like, make a conjecture about something, and I often have students look at me and say, what's a conjecture? All a conjecture is a statement or conclusion that has not been proven. So something you want, it's like a hypothesis. You think science, right? When we hypothesize about something, that's what a conjecture is. A lot of times it's something we believe to be true and then we're attempting to show that it is. Or maybe we don't believe it's true and we're attempting to show that it's false. Okay, so it's usually something that we kind of have an idea about to start with. Inductive and deductive reasonings are two different kinds of reasonings. Inductive reasoning is a method of making generalizations based on observations or patterns. Okay, so you make this observation that all the little boys in the class are a little bit wild and a little bit hyper, and all the little girls are a little bit calmer, and somehow you make this generalization that all boys are hyper and all girls are calmer. And you may be right, and you may not be, right? That's your conjecture based on this experience, but it's based on an individual experience. The second one is deductive reasoning, and deductive reasoning goes the other direction. You're actually using a series of either axioms or theorems or definitions, undefined terms, and you're actually going the other direction. You actually know something's in general always true, and then you can make the claim that it's true about a specific case. Okay? So instead of going from specific cases and making a general statement, you're going from a general statement, and now you're saying, well, that's a true statement then. So for instance, if you actually, sorry, just a second. Okay, so sometimes you can do this with deductive reasonings is that you have properties. Okay, so we're going to see some properties happen once we get to chapter 3, I think it is. And some of these properties are going to be things like the distributive property. You're always allowed the distributive property to distribute the first number across a set of parentheses with an addition or subtraction inside of it. And so since you know that that is a generalized rule, it doesn't matter what numbers I put in anywhere, it's going to work. Okay, so that's actually deductive reasoning. A counterexample is something that shows a conjecture false. So I had my sort of conjecture a minute ago that all the little boys are hyper and all the little girls are calmer. All it takes to make that statement false is to find one hyperactive daughter, right? One hyperactive little girl, and all of a sudden my generalization is not true anymore. I don't have to have all the girls more hyper than the boys. I just need one. And that one is called a counterexample, right? So one of the things we're going to take a look at in this section is sequences and series. In particular, we dealt with series last section where we added things together. What we're going to look at now is sequences, is where we're not going to be adding them, we're just making a list of them. That's the difference, okay? So in specific, we're going to talk about 3 different kinds of sequences, I think, 2 in detail. The first one is an arithmetic sequence. So a sequence is actually just an ordered arrangement of numbers, figures, or objects. So we tend to think, since we're in math, that we're talking about numbers. But that doesn't always happen. When you're working with the very little ones, they do things with shapes and colors a lot, right? So they see red triangle, blue square, red triangle, blue square, and the question is, what comes next? That's a sequence. Okay? And it gets more complicated after that, right? We see red circle, blue triangle, red circle, blue triangle, red circle. What comes next? Red circle. So they get more complicated. So it doesn't have to necessarily be numbers, but we are going to look specifically at some cases with numbers, also some cases without. A couple of them that we're going to look at that are going to have numbers. One of them is arithmetic sequence. So in an arithmetic sequence, what we have is we have one number followed by another one, and the way we get from the first number to the second number to the third number is we add a constant value. And you've seen these before, so it looks something like this. If I had 5, 8, 11, 14, what number am I adding from one term to get to the next? 3. Because there is a constant number that I add from one term to get to the next, that makes this arithmetic. So I can put a +3 on all of these. That number that I added is called the common difference. Okay, it's the difference between the two numbers. It's the number I would add or subtract depending on which direction I was going in my sequence. Okay, so this number 3 in this case is my common difference. So far, so good? All right. A recursive formula is a formula based on patterns that just shows you how to get from one to the other. For instance, if I were talking about that sequence that I just created right here, the recursive formula, or at least the description of it, would be we add 3. That doesn't tell me the sequence. It just tells me how to get from one term to the next term if I knew one of the terms. Does that make sense? This idea of I add 3 is this idea of being recursive. An nth term actually tells me how to physically get each one of those terms. Okay? Obviously, it's going to be involving the add 3 business, because that's how I get from one to the next. The problem with the description of just add 3 is, well, starting where? Do I start at 1? Do I start at -7? Do I start at 3.6? I don't know. So I have to figure out how and where I start before recursive formulas are helpful. But an nth formula works all the time because it actually tells you in there where you start and how to get to the next term both. So I want to use this example that I just created, and I'm going to show you how to get that nth term for this example. Okay? So we already said we add 3. Agreed? So the way that this will work is that 3, in fact, let me actually think with you for a moment back to when we did the Gauss situation over here. When we did this Gauss situation over here, we added a number together a bunch of times, didn't we? This idea of recursively adding something together. And you see this idea down here as well. We're adding the 3 to something a bunch of times. Well, what is a simpler way than adding something a bunch of times, the same thing? Multiplication, right? At some point along the lines of 2nd grade now, folks, children learn to multiply. Okay? So, somewhere when you're multiplying, the first description is, if I wanted to add the number 3, use 3 as this example, together 5 times, it'd be easier to multiply 3 times 5. Agreed? So it becomes a multiplication pattern. So what we see when we do the nth formula is we see that 3 multiplied by the n that we're talking about. Okay? It becomes a multiplication factor because it's got this repeated addition business going on. Okay, so are we good with that so far, the 3n? Okay. Now the problem is, or what the goal is, let me say that first, is what I'd like to be able to do is to plug in n equal 1 and actually get 5. Because my first term, n equal to 1, is 5. Problem is that if I put n equal to 1 into 3n, I do not get 5. What do I get? 3. I get 3. Okay? Which is exactly how many too few? 2. So what do? I add 2. And that's all it takes. And you can test to make sure that it will work by just doing the next one. So if I put in now n equal to 2, so what if I put 2 in here? 3 times 2 is, plus 2 is, there's your 8. Okay? Let me just tell you, there are formulas for how to do this, like actually written down, like you put this number in here and you put that value here, and there's a formula relationship thing. I have no idea what it is. Not joking, because it's not necessary. It's easy to look at this and to say, okay, well, the common difference, this particular number is a multiplication factor, and then how many more do I need to add or subtract to make it work? And that's how we can approach it. Okay? I want to show you an interesting sequence. We're not going to do a lot with it. I think there's one problem that you have that's going to bring it up. I can't remember. But I want to show you the Fibonacci sequence. Have you seen or heard of the Fibonacci sequence before? Show of hands if you've seen or heard of it. If you haven't, it's okay. Okay. This is not arithmetic, right? To get from 1 to 1, I don't do anything. And to get from 1 to 2, I add 1. And 2 to 3, I add 1. But to 3 to 5, I add 2. Well, that's not helpful. It doesn't have the same number added every time. And you're going to find out very quickly that the other option that we have, which is a multiplication option, doesn't work as well. I can't multiply these numbers. I can't multiply 1 by something to get 1. Well, I can. It's 1. But then 1 times 1 is not 2. So there's not a multiplication factor that will work either. But those of you who've seen this before, do you remember how you do it?
Add the
You guys are doing great. All right, so if I add 1 and 1, what do I get? 2. If I add 1 and 2, what do I get? 3. If I add 2 and 3, what do I get? 5. So the way that I get the next term is I add the 2 previous terms. So I can figure out how to finish the sequence or continue the sequence anyway after this. What do I do to get the next term after 21? I add 13 and 21, and what would that be? 34. And what would I get next if I wanted to keep going? 55. Okay. Fibonacci sequences are found all over in nature. So they do occur in our natural world. It's not just like somebody made it up. Fibonacci is the one who discovered the pattern itself, but he didn't create it. Okay? All right. The other one I want to talk about is a geometric sequence. So an arithmetic sequence is where we add a number every time to get the next value, right? That's the one we just did. A geometric sequence, we multiply by a number every time to get the next value. So a geometric sequence gets much bigger much more quickly because I'm multiplying. That's one feature about it. It gets much quicker. So and even quicker than geometric, which we're not going to deal with, is called exponential. Exponential growth is even bigger, faster. So you may have heard this phrase before, that rabbits multiply exponentially. That's actually from a mathematic term. So geometric happens faster than arithmetic, however. And this number that you multiply by to get the next term is called the common ratio. Okay, ratio is a term that we were using for fractions sometimes. It didn't have to be a fraction, but in this case, what we're looking at, and I'll get done to this a to the n in a minute, but is, let me do a sequence for you. Let's say we had 2, 6, 18. I'm going to stop there. So if you were looking, if this is arithmetic, you would say 2 plus what is 6? 4. But 6 plus 4 is not 18, so it's not arithmetic. So your only other option when you're looking at these for deciphering is multiplication. If I multiply 2 times what is 6? And then 6 times 3 is 18. So I can actually do this one with multiplication. I'm not sure why my favorite number today is 3, but we'll go with it. So we multiply by 3, and we could get the next term, right? At least in theory, we could do 18 times 3, and we can continue the process. Agreed? There's a way to continue the process. Again, this idea of multiply by 3 is a recursive idea. Much like the Fibonacci sequence, add the 2 previous numbers, is a recursive idea. No matter where I start, I could do that. I just have to know where to start. However, with the geometric sequence, just like with the arithmetic sequence, I can get an end term. I can know where do I start and what happens next. Okay? I know what happens next. I multiply by 3. But the question is, how do I involve the where do I start part of it? So let me show you. The number that's the common ratio is going to be an exponent base. So in this case, it's 3. So up here, I've got a definition of what it means for something to be an exponential, a to the n. All right? So an a to the nth power actually just means the a is multiplied by itself a whole bunch of times. How many times? N times, because that's the exponent. So if you were talking about a to the 5th, it would mean that I have 5 a's all multiplied together. If a were to the 10th, I would have 10 a's all multiplied together. Okay? There's a few features. If n is 0, we're going to talk about this more later on. It's in chapter 3. If you have an exponent that's 0 and the base is not 0, and in fact our base is not going to be 0. There's a couple of features for the common ratio for this to make sense. Is that typically speaking, we're not talking about 0 or 1. It could be, but it's sort of a default weird situation. It would look really odd, okay? And you're going to ask some questions about that later. But usually we're talking about values that don't have a base here of 0. So if the base is not 0, but the exponent is, in other words, if I had 3 to the 0 power, it would be equal to 1. Okay? Anything to the 0 power is 1. And I promise I'm going to show you why, but it's just not going to happen today. Okay? We need some more math to get there. But what I need is I need an exponent. I need something that is up high. And here's what I need. I need an n minus 1. So let me talk about why. What happens when I put the number 1 into n minus 1? What's 1 minus 1? 0. And then what would 3 to the 0 be? 1. That is really helpful, and here's why. The other thing I can do to get the rest of my pattern is the first number in my sequence, I put at the front. Why? Well, because if I put in if I put in n equal to 1, I get an exponent of 0. 3 to the 0 is 1. And then the 1 times the 2 is 2, which is what I wanted it to be. That's why it works. So always on the outside is your first term. Always on the inside is your common ratio. And then always as your exponent is n minus 1. That one's actually a little bit more straightforward than the other one. I don't have to figure much here. Not that I had to do a lot. I just had to do adding and subtracting on the other one. But still, I had to figure what that plus whatever was going to be at the end. Here I don't really have to do that. And you can test to see that it works, right? So I already tested out loud for n equal to 1. So let's try n equal to 2. What if you put n equal to 2 in? Well, you'd have 2 times 3 to the 2 minus 1. Reminder, where do I start in this? Do I multiply 2 times 3? No, I do not multiply 2 times 3. You have something called order of operations, and even though they're not actually there, there is an understood parentheses up there in the exponent that you have to do the simplification in the exponent first. So what is 2 minus 1? 1. 3 to the 1 is 3, and then 3 times 2 is 6. And lo and behold, that's exactly what you have for your second term. And the third term will work as well.
Wait, what? The n changes y?
This right here, n, represents what term am I on.
Okay.
So if I want to find the fifth term in this sequence, I don't have to multiply by 3 2 more times. I could put the number 5 into this formula that I've created. 5 minus 1 is 4. I can raise the 3 to the 4th power and multiply by 2.
And that gives you the number in the sequence?
That will give you whatever term it is in the sequence that you're looking for. Back up.
So say like the pattern is you multiply by 4 each time, it would be 2 times 4, and then
N minus 1, right. Yep. And we're going to do a couple more. In fact, I think that's my next slide. So let's take a look so that we can practice on a couple more, okay? All right. What we're going to do first is it says list 3 terms that continue the sequence. So we're going to find the next 3 terms. And then we're going to find out is the sequence geometric or arithmetic, which we will find out in the process of listing the next terms, by the way. And what we're going to do last, even though the directions don't say it, because some of your directions will, is we're going to find what does the nth term look like. Okay, directions are not on there for doing that on this one, but some of your questions in your homework have that. Sound good? All right, so take a look at the first one, 1, 4, 7, 10. What do you notice? It's an addition of 3, isn't it? So even though I'm going out of order, I think you can probably tell me. Is it geometric or arithmetic? This is arithmetic. So can we figure out the next 3 terms? What comes after 10? 13? 16? 19. All right, we good with that? All right, good. Now, this is the part of the directions that aren't on the directions because I want us to practice. We're going to find the nth term. All right. So, to find the nth term for an arithmetic sequence, what do I do? Okay, that's good. So where's the 3 coming from, Katie? It's from the plus 3. That's that common difference. That is multiplied by n. Okay, again, because of this repeatedly adding something is the multiplication factor. But this isn't quite right yet. What else do I need? Right, and why do I have to make it equal to 1, Merely?
Because that's where you start.
Yeah, and it's not always going to be 1, but in this case it's 1, right? Because this, whoops, I wanted that in red. This is a number 1. So what I want is I want to be able to plug in the number n equal to 1, because n, remember, represents what term am I on. So if I want to put in the number 1, it means I'm finding the first term. But if I put the number 1 into 3n, what do I get? 3, which is not what I want. I want 1 because it starts at 1. So I'm going to do minus 2.
So we're trying to get the first number in the sequence.
Yeah.
It doesn't matter what number it is.
It doesn't matter what number it is. We're trying to get, when I plug in n equal to 1, I'm trying to get the first number in my sequence. So far, so good? So let's test to make sure it works. That's a good thing to do. This is one of those like problem-solving strategy, step number 4, check and make sure it works things. And we can check to make sure it works by plugging in another n equals that I know. N equal to 2, n equal to 3, it doesn't really matter. Smaller the better because you can do it in your head. So I'm going to suggest n equal to 2. What if I let n equal to 2 here? What do I get? 4. And n equal to 2 should be my second term. Is my second term 4? Yes, it is. So I have the right nth term because it worked for another pattern, another number in my pattern.
So we could just plug in whatever number, like if we have 4 of them up there, we could just do like 3 times 5 minus 2 and we can get the 13. So we could keep going in the sequence.
Yeah, and the benefit for that is, let's say Nicole, I mean, like, I asked you to find the next 3 terms, but what happens if the question asked you, what's the 100th term in this sequence? If you really so desired, I suppose you could get your calculator out and add 3 100 times. Not 100, but like 97 or something. That would take a while. It would be tedious, and to be honest, you would probably not like me very much if I had that as my only option, right? But this is really easy, because if I've got my nth term, that is, if I've created my nth term, I can just plug the number 100 in. And I would say, oh, 3 times 100 minus 2, and I'd have my number.
They used to have this on the test at like the state test, and they never taught us this, and I always got them. I remember not having this.
The good news is now you know. And you know what? I'm glad you actually mentioned that, because we've actually had a lot of feedback on students going to take the OGET. So I know some of you have already done that. But that a lot of the things that we're currently teaching in Math 1, 2, 3, which we should just pat ourselves on the back, Dr. Marsh and I, are showing up on that test. So that's a really good thing, because you guys are actually taking this at, hopefully, if some of you are still looking towards taking the OGET in the next year, you'll have had some of these experiences, and that's really good. Okay. All right. Let's look at the next one. What do you see about the next one?
It's multiplied by 2.
Yes, it is. Very good. It is. It's multiplied by 2, right?
Yeah.
So multiplied by 2, does that make it arithmetic or geometric?
Geometric.
That is geometric. Excellent. Can you find me the next 3 terms? What comes next? 48.
96.
Excellent. And if I ask for the next 3 terms, I don't need an nth term to do that. We can do that pretty quickly, but if I ask you for the 100th term, that's where things are getting a little bit unhelpful to use this recursive idea of just multiply by 2 each time, right? So we're going to come up with an nth term. So my nth term is what? How will it start?
2n.
Okay, we've got 2 inside of the parentheses. 3 on the outside because it's the first term. And the exponent is n minus 1. Okay, I already went through why that works. Let's test to make sure we got the right formula by plugging in n equal to 3 this time just for fun. Okay, so let's suppose we do n equal to 3. If I put in n equal to 3, I've got 3 times 2 to the 3 minus 1. 3 minus 1 is 2. 2 squared is 4 times 3 is, and look back here, that's my third term. So it worked. We have the right formula. Okay, here's the question of the day on what we just did. Now, I only spoke about it in brief, but is this inductive or deductive reasoning? Hang on, let's give everybody a chance to look back and think about that. I don't want you to answer right away. Which type of reasoning is that? I think it was on page 1. Yep. So what is deductive reasoning?
Because we have the specifics and we're looking for the general rule.
Okay, so when we have the specifics and we're looking for the general rule, which one is that?
Oh.
Look back at the description. What does inductive say? It's inductive. Inductive is making generalizations based on observations or patterns. So I'm starting with an observation, I'm starting with a pattern here, and I'm making a generalization, i.e. that nth formula. That's my generalized formula. So this is actually inductive reasoning. I'm taking a pattern and I'm making a formula that says this is how it will always work now. Now, we have a pretty good idea that our pattern always works. I mean, we've tested some things otherwise, right? We tried n equal to 1, we try n equal to 2. We have a pretty good idea that this continues and this is going to work. But it is one of those things that could go wrong in certain situations. For the patterns that we're looking at, that's not going to happen. But when you do inductive reasoning, that is making generalizations based on previous patterns, you can be wrong, okay, in general. We're not going to have that happen, but it could. All right. Next question. We're going to actually start now a little differently. This question says, find the first 5 terms of the sequence with the nth terms as follows. Label each as arithmetic, geometric, or neither. All right, so the first one. What would the first term in my sequence be? How would I find that? It'll be 11. How'd you get 11? You put in n equal to 1. So put in n equal to 1, I have 5 times 1, which is 5, plus 6, which is 11. What's next?
No.
What is it? 16. Yeah, that's right.
I don't know.
How do you get 16?
Because you put the 2.
You put in n equal to 2. Okay, so the first one is n equal 1, because it's the first term. The second one is n equal to 2, because you put n equal to 2.
Dividing 5.
Yeah, well, let's do one more to make sure, right? What would happen if n equals to 3? You get 21. And so Leah suggests that I'm just adding 5 every time. Does it look like that? How do we know for sure that we are? Can you tell?
You subtract 11 from 16.
What did you say, Hannah?
Because the formula works.
The formula actually looks like the formula we keep using and creating for the arithmetic, doesn't it? It looks like a number times n plus or minus something else. So it's actually got the right pattern for it to be arithmetic. It is arithmetic. I am adding 5 every time, and I'm adding 5 every time because it says 5n. That's why. So this is arithmetic. I'm not done with my 5 terms. Once you know it's arithmetic, you can stop plugging numbers in if you'd like, and you could just add 5. What would come after 21? And then, right. And we could keep going, but we're only asked for 5 of them. All right, we'll do the last 2 slides here, or the last 2 on this slide, and we'll be done. What do we do for the next one? I'm going to plug in, same directions. So I'm going to plug in n equal to 1. So what happens when I plug in n equal to 1 into n squared minus 1? I actually get 0 on that one.
Yep.
What happens when n equals to 2? That's 3. What happens when n equal to 3? 8. Good. N equal to 4? 15. And n equal to 5 is 24. All right, so let's take a look. Arithmetic, geometric, or neither.
Uh-oh.
Arithmetic would mean I can add the same number each time. Does that work? No.
Oh.
Geometric would mean that I could multiply by a number to get the next one. Does that work?
No.
No. In fact, geometric blows up immediately because I've got a number 0, and I can't multiply 0 by anything to get 3. So I'm out of luck immediately by the fact that there's a 0 in there. So that means this is neither. And it's also neither because take a look at that formula for the nth term. Does it look like either of those formulas I've been creating? No. Those formulas either had n times a number or the number n, letter n, in the exponent. And this is neither. This has the n as the base of an exponent of 2. All right, inductive or deductive reasoning?
It's
This is deductive. We are starting with a generalized, value or form or whatever. I'll circle it. And we are creating this specific pattern from it. That is deductive reasoning.